And as we usually do on Wednesdays, I thought I would go through the theory of the week, you know, the stats stuff of the week to make sure everybody has a good, strong foundation in what we're doing and how it works and that kind of stuff. And then we'll jump into homework questions and how to do these things in SAS or TI calculators in Excel. Because especially with probability, there are a lot of easy ways to do these things without using SAS. So it's good that the school no longer mandates that you always use SAS. So, all right, let's just a quick reminder that I did grade everything. So if you're not seeing your grades, let me know, because I have to manually like post them, and sometimes I forget to do that. So let me know if your grades aren't showing up, and I'll go back into the grade book and make sure that I've actually posted them. And as always, my comments are always within the stuff with track changes and that. And well, it's not track changes. You got to go in and you got to do the whole speed grader thing, and then you can see it in speed grader. It's a weird thing, but I think you're all getting used to it. Okay, the most important thing that I think a lot of people have forgotten, because I haven't seen a lot of these posts yet, is that your main research article post, your summary of that article, is due tomorrow night at midnight. And that's midnight, you know, local school time, which of course is Eastern time. So make sure that you have found your article and you have summarized it, you know, and answered all the questions that it asked you to answer. It has you discuss the research questions and the hypotheses and the statistics summaries that they did and the different types of statistical analysis they did and that kind of stuff. So make sure you're getting that posted in the discussion board no later than Thursday. You are supposed to also submit it to Turnitin, and the instructions are there in the body of the instruction. So let me know if you're having trouble with that. There's been some difficulties within the past, but it should be hopefully working. And then of course your 2 replies, right? You have to reply to 2 other posts from your classmates. Those aren't due until Sunday. So that's why we mandate that everybody has to get their stuff posted by Thursday, because then it gives you guys some, you know, some time to go in and read somebody else's post and then make some sort of thoughtful, you know, follow-up question or reply or whatever, you know, because if everybody just posted on Sunday, you wouldn't have time to do it. So make sure you're getting those in, because last time I checked, it was only about 1/3 of both classes total had done it. Okay, so let's talk about the actual concept this week, which is probability. And the first kind of probability questions you're going to see are the very basic ones that are called and probabilities. So for instance, you know, what's the probability given this data in this table? What's the probability that somebody, and by the way, that's not 192, that's an L from the total. That there's something's going on weird with the way it's displaying. The L in the total is going on to the next line for some reason. That's just 92. But anyways, and questions are really easy because well, probability in general is very simple. And it can get very complicated, of course, if you're in a very complicated, you know, advanced probability class, like some of the ones I took in grad school that made my head hurt. But for the most part, you know, the probability of any kind of event is simply just good over total, where good is just the number of ways, you know, that the event can happen. And then the total is just the total ways that the event can go. So for instance, if we said, you know, what's the probability of getting a yes? Well, that's pretty obvious. We go up here and we get the total yeses, which is 92. So that means we had 92 good results, right? Things that did what we're looking for, i.e. said yes. And then the grand total was 227. So it's as simple as that. And then you stick that in a calculator and you get it as a decimal, right? And you write it as a percentage, because usually probabilities are presented either as a decimal or as a percent. Sometimes they're represented by a fraction, but only when those fractions are common, like 1/2, 1/3, 1/20. If you went up to an average person and said, how big is 92 over 227? They'd be like, I have no clue, right? You'd want to give it to them as a decimal, and then they would have an understanding of how big that is. So when we do an and question, we say, what's the probability that it's yes and red? Well, that just means it has to be both those things. So we can't look at all 92 yeses. We have to look at the yeses that were also red. And so now it's simply 32 over 227. And it literally is that easy and that simple. Don't make it harder than it has to be. Questions so far? Okay. So here's some examples that I've written all over, of course, but we've already done some, so we don't need to worry about those. Okay, what about or questions? Well, just like the and questions, there are these formulas involved, this whole A plus B minus A and B all over the total. That's an or question. And what they're basically saying is, if you're doing an or, you can add up all of the A's, then add up all of the B's, but then you have to take away their intersection because you've added those twice. So for instance, the yes or red. Well, here's 92 for all the yeses, right? Here's 82. Again, something's going on with these slides, but there's 82 for the reds, right? So here's 92 and 82. But 92 was basically counting up all three of these things, right? And then 82 was counting up all three of these things. And we can see that 32 was counted twice. So that's why they come along and they subtract the 32 and they do 227. Well, that's fine, in theory, and that's fine for us to understand, how it works. But really, it still comes down to good over total. Just be smart about how you count up your good and how you count up your total. I mean, in this case, total's easy. It's still 227. But when you're counting up your good, you could have just as easily gone, well, I'm going to count up all the S's. So 50 plus 32 plus 10. Then I'm going to count up all the reds that I haven't already counted. And then I'm going to add in the 20 and the 30, and that's going to be my total, right? And I don't have to do this whole subtraction thing. So it just depends on how you want to attack it. It's still going to be the same thing. Good over total always works, just as long as you're careful and you count up accurately and you don't overcount things, you don't miss things, that kind of stuff. So you just need to be systematic about how you count. Now, conditional probability, given something, and that's what this little vertical bar means. So this is the probability that A happens given that we know B has already happened. So this first example says, what's the probability that we get a yellow, I don't know what these are, maybe these are marbles or something with votes on them. We get a yellow marble given that it was from, the yes bin. Well, if we know that we're picking from the yes bin, then we know we're only picking from these three choices, and that's why our new total is only 92. Because the given condition narrows our focus, and we're no longer looking at all 227 things. We're only looking at those things that have the given condition. In this case, we're looking at the things that are yeses. So that's where we get 92 for a total. And out of those 92 things, how many of them were yellow? 50, right? So there's our 50 over 92. And you can see that yellow given yes is not the same thing as yes given yellow, because now that we're doing yes given yellow, we know that we're in the yellow category instead of being in the yes category. So now we know we have all of these to look at, and we have a new total that's only 90. And then out of that total, what's the good? Well, in this case, the good is still yes, right? Because of the way that we worded the question. But now it's 50 over 90 instead of 50 over 92. So that's how simple conditional probability is. Yes, there are these big complicated formulas where you do the probability of A and B, divided by the probability of B and all this crap, and fine. Be my guest, learn the formulas. But they really aren't necessary if you just think about it and just think about good over total, especially when they give you the numbers in a table. My God, if the numbers are in a table like this, probability is so simple because it's just a matter of circling stuff and highlighting stuff and picking out stuff and going, okay, there's my good, there's my total, blah, 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 bang, I'm done, right? So probability that something is a no, given that it's blue, well, now we're dealing with just the blue things, right? So that's why my total is 55. And out of those blue things, how many no's do we have? There's the 5, right? Probably that's a maybe, given that it's red. Again, so we're looking at all the reds. So that's why 82 is our total. And out of all of those reds, how many maybes do we have? 30. It's just that simple. Okay, questions so far on these? All right, moving on. The complement of an event is everything outside of that event. So everything other than that event. So for instance, the complement of red is not blue. It's blue or yellow, right? It's everything else that isn't red. The complement of yes is not no. It would be no or maybe, right? It's all the other stuff. So complements always have to add up to the entire total. So if you think about, your 227 things, in this case, you can visualize them as, colored pieces of paper with words on them, right? You got yellow pieces of paper with yes, no, or maybe, red pieces of paper, right? Blue pieces of paper. You can think of them as marbles with these words on them. However you want to visualize these things, they're in a big bucket. And a complement is, well, if you take all of one certain type and take it out of the bucket, whatever's left in the bucket is the complement, right? So if you pick out all the yellow pieces of paper, whatever's left behind is the complement of the red. If you take out all the blue pieces of paper, whatever's left behind is the blue pieces, right? If you take out all the pieces of paper that say yes, then whatever's left behind is the complement of yes. So that's what it means when you see a little horizontal line over something. That means the complement. There are other ways to write complement. Our book, I believe, tends to do this for everything, right? So, A with a line over is the complement of A. Other books will do a little squiggle and an A. I've seen this symbol and an A. I've seen A with a C above it. That's a C, right, for complement. I've seen A with a subset C. So I've seen all sorts of different ways to represent a complement. I have even seen A with a little like a little apostrophe, almost like if you guys remember, well, if you ever took calculus, it's almost like saying the derivative of A, which of course is nothing similar to a complement. But those are the various different symbols you might come across as you're reading up in your research papers or in your future lives, and they're talking about the complement of something. They will use different symbols. The bar over the top is by far the most common version. I kind of put them in order, actually. The little squiggle is kind of second. The little line with a little thing on it, it's almost like a sideways L. That's kind of the third, and those other ones show up very rarely. But it all depends on the author's preference, I guess. Okay, discrete versus continuous variables. We've talked about this before. Discrete things are counted. So one thing to help you remember is discrete numbers are always counted. And continuous numbers are always measured. Now that does not mean that continuous variables always have to have decimals. It just means that they can have decimals. And it does mean that discrete numbers never have decimals, right? So if you see just a set of data that are all whole numbers, like the first one, you know that could be continuous data and it could be discrete data. You need to know more about it. However, if you saw the second set of data with decimals in it, you would know right away that that would have to be continuous data, because discrete data is always whole numbers. Continuous can be both, but it's more often than not continuous will have decimals. And the reason why I say it can be both, let's say you went out and surveyed a bunch of people, right? And you had them fill out a survey, and you asked everybody for their weight or their height. Everybody's going to answer a whole number. Nobody's going to tell you they weigh 135.72 pounds, right? It's just going to be, I weigh 135 pounds, that type of thing, right? Nobody's going to tell you they're 6'4.5" They're 6'5", right? Or they're 6'4". Humans are always going to round. So even though both of those variables, your height and your weight, are continuous variables, because technically you measure your height and you measure your weight, and you can measure them both to as much accuracy as you want, right? The more accurate you get, the more decimal places you're going to get. But if you were to survey people, they would just go ahead and round, and then all of your answers would be whole numbers, and it would appear as if you had discrete data, but you really don't, right? So the rule of whether or not something is discrete or continuous doesn't come from the appearance of the data. It comes from the source of the data. Basically, what was the question involved to get that data, right? What was the variable? So if you're asking for someone's age, that's actually a continuous variable, because again, somebody's just going to say I'm 35 years old, or I'm 42 years old, or I'm 18 years old, or whatever they are. But age is a measurement of time, right? You can go from years to months to weeks to days, and so on and so on and so forth. So you could measure that in smaller and smaller increments. So that is a measured continuous data variable, even though the values that are going to be assigned to it are going to be discrete for sure, because nobody's going to say, oh, I'm 35 and a half years old. So just keep that in mind. Okay. Probability distributions. A probability distribution, there are two types of probability distributions. There are discrete probability distributions, and there are continuous probability distributions. That's why we spent so much time talking about the difference between discrete and continuous data. Discrete probability distributions are built upon questions that result in discrete data, i.e. something that's been counted. And so the possible values that you can get for your variable will always only be whole numbers, and there will be some sort of limit. You couldn't get an infinite number of them. What I mean is the value couldn't go on and on and on forever. There's going to be an upper bound to your numbers, and there's normally going to be a lower bound. And since you're counting things, the lower bound is almost always zero. You can't count negative things, right? So probability distributions for discrete numbers almost always start with zero. You'll probably never see one that doesn't. And then they have a finite number of values, because it'll be a question like, how many times a week do you eat out? Well, that answer is going to be somewhere between 0 and 7, right? How many kids do you have? Well, that's going to be somewhere between 0 and, I don't know, the largest family is probably in a 35 or something like that, right? But it still has a cutoff. And for most people, right, for like 99.9% of your data, if you ask them that question, the upper bound would probably be like 6. So that's the idea of a discrete probability distribution, is you have a variable, i.e. a variable you can think of as just a question that was on a survey, and the values that variable can take will just be the different answers that you could get from that survey. And then the probability distribution just shows you how likely each of those answers were. So for this particular question, 10% of the people answered 0, 25% of the people answered 1, 45% answered 2, and 20% answered 3. What do you recognize or notice? What do you notice about all of those probabilities? And more specifically, what do you notice about the sum of those probabilities?
They add up to 100.
Very good, Cheryl. Yes. And in order for something to be a probability distribution, its probabilities must always sum to exactly 1, right, or 100%, right? So if you added up these decimals, they would add up to exactly 1, which would be the same thing as 100%. Okay, so here's some other rules, right? In order for it to be a probability distribution, you have to have at least 2 different outcomes, right? Like a yes and a no kind of thing. Probability of no more than 2. I don't understand what the hell that means. I've never, probability of no more than 2. Oh, I'm sorry. These are actual questions. They're not telling you rules. So this is asking, can you calculate the probability of at least 2? Well, that would be 2 plus 3, right? Because at least 2 would be 2 and greater. And then probability of no more than 2 would be up to and including 2, right? That's less than or equal to 2. So that would be 0 plus 1 plus 2. And then they could say probability of greater than 2. So they're basically showing the 3 different things. You can talk about something being strictly greater than something being at least something, which is the same thing as greater than or equal to, and then no more than is the same thing as less than or equal to. So it's just reminding us that we know what these things mean in English, right? So we're looking for x that is greater than or equal to 2, and down here we're looking for all the x that are less than or equal to 2. And then, of course, we would have, you could have the word just less than 2, which would be x is strictly less than 2. So those are, the four options when you're calculating these things. Okay, only 2 outcomes on each attempt, repeatable, same probability of success on each attempt, and the variable counts successes. Those are all the rules that are necessary for something to be a binomial probability distribution or a binomial experiment, right? Bi, like a bicycle, meaning 2 things. So it's really, it's a special version of a discrete probability distribution where you only have 2 outcomes instead of, in this case, 4, right? You only have 2 things, a yes and a no kind of thing, a success and a failure. So, for instance, if you're rolling a die, we know that there is a 1/6 chance of rolling a 5 on each attempt. And so n is going to equal, capital N is going to equal the number of times that you roll the die. So that's your sample size base. That's how many times you run the experiment. And then X is always going to be the number of successes that comes out of that experiment. So in this case, it's going to be the number of times it comes up a 5. And you can see that this is a binomial experiment. Even though the die itself has 6 outcomes, right? The numbers 1 through 6. The way this is worded, this is a binomial experiment because either we get a 5 or we don't get a 5, right? So anything with multiple outcomes can be turned into a binomial by thinking about something being its success and then the complement of it, right? Everything else being the failure. So that's the nice thing about binomials is we can make just about anything fit a binomial. There's a pretty simple formula for binomials. But again, you don't have to memorize this because we have technology to do it for us. These little exclamation marks just mean a factorial. So you take the sample size, the n in the previous example, right? So in this case, if n is 10 and x is 3, you would have 10 factorial. And that just means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? That's what a factorial is. And then on the bottom, you would have 3 factorial, and then n minus 3, which is 7 factorial, and you get a lot of cancellations, and this always comes out to a whole number, all this junk, when you do the math. And then pi here is the probability of a success. So if we were doing the whole rolling a die thing, pi would be 1/6. So it's 1/6 to the power of how many successes times its complement, 5/6 to the power of its complement, right? So if we wanted 3 successes out of 10, then this would be the other 7 that didn't come up the way we wanted them. So that's the basic binomial probability formula, and how we would plug everything in and how we would get an answer and see that it's about 20% chance. Or we just do it in SAS with this nice simple formula, and this stuff is all in that SAS how-to thing. It's been there the whole time. If you copy and paste it, just be careful, and I've said this before, anytime there are these quotation marks, oftentimes when you copy them across, they copy over as the curvy ones, and the curvy ones don't work. You have to go in, you have to delete them and put in the little sharp ones, and then the code will work. And you can tell because when you copy it over, all of a sudden the code turns a different color. It gets all wonky because it doesn't like what it sees. Okay, so if you want to, guys, you can by all means do these binomial questions with the formula and a calculator. You can use SAS. You can also use, Excel does binomial distribution. It's binom.dist for the newer ones. It's binom.dist without the dot if you have an older version of Excel. If you have a TI calculator, or any of those graphing calculators, they all do binomials really easily. So the hardest part about these is knowing when to use which. So we have 2 formulas in SAS, and we also have 2 formulas in Excel and in calculators. You're either doing the PDF, the probability distribution function, or the CDF, which is the cumulative distribution function, so it accumulates things, right? So this one gives you the precise probability of exactly one thing. So if you want to know the probability of getting exactly 3 successes out of 10 trials, you would use the PDF version of the SAS code. If you want to know the probability of getting 5 or fewer, right, less than or equal to 5 successes, you would use the CDF with x equal 5. And what the CDF function does is it adds up the probability of 0 successes all the way up through and including x. So since you wanted less than or equal to 5, you would set x equal to 5. And it would count up 0 plus 1 plus 2 plus 3 plus 4 plus 5. It would count up all those probabilities. Now, if you wanted the probability that x was less than 6, you would do the same thing. You would just do 5 because it would count up 0 through 5, because less than 6 means 0 through 5 when you're talking about discrete probability distributions, which is what a binomial is, right? You can't have 5.5 or 5.7 or 5.9, right? It's either 5 or it's 6. So less than 6 is the same darn thing as less than or equal to 5. Now, what happens if you want greater than? Well, that's easy. If you want greater than something or greater than equal to something, just know that you're going to use a CDF and then subtract it from 1. So for instance, if you wanted to do the probability of greater than 4, well, that's 5 and above. So if you put 4 in for x and run the CDF, this is basically going to give you the probabilities of 0, 1, 2, 3, and 4 all added together, right? And because you wanted greater than 4, you want everything else. So you basically want the complement of this. So whenever you get this answer, you just subtract it from 1. And the same thing here. If you want greater than or equal to 5, well, that means you want 5 through 10. So what's left? 0 through 4. So you do the same thing. You do the CDF with 4. It gives you this number. You subtract that from 1, and that gives you the number you're looking for. So whenever you're doing greater thans or greater than equals, just know that you're going to have to do the CDF function and then 1 minus it to get what you're looking for. Okay. We can calculate the mean and the standard deviation of probability distributions. The mean and standard deviation for a binomial probability distribution is very easy. It's simply just n times p, right? So n is the number of trials, p is the probability of success, and then the standard deviation is just the square root of n times p times its complement. That's 1 minus p. So those are really easy, and we need those if we want to start doing approximations to the normal curve, which you have to do in some of your questions. Then there is the Poisson probability distribution. And this one counts up the number of things that happen like in a time interval. So it's a slightly different thing, but it's very similar to the binomial. And so the code is also very similar. You're still doing a CDF, but this time you're just putting in Poisson here, right, instead of binomial. And then you've got a U and an X. So instead of an N and an X, you've got a U and an X, and then you can do the Poisson probability distribution. It's very, very simple in SAS. And again, this code is also in the how-to thing. All right, that's it. Questions? Okay, then let's end the slideshow and go through any specific questions you might have on the homework, or if you're working ahead on the final project or whatever. What do we got?
I do have a question, Dr. McBride, but
Yep.
I want to give the opportunity for people to ask questions first because I want to ask a question on week 5.
Okay.
Can we look at, I have 2 questions. So I'll start with 446, part D.
Sure.
Can we just go through how to?
Yeah, absolutely. All right. 446 part D. Okay. So we want to know the probability that none of the 20 return products has any sort of defect. So that basically means that all 20 of them were in good shape, right?
Yes.
So we're
Oh,
looking.
Okay, I think I just read it wrong.
Yeah, and really that's the hardest part about these is making sure that the English phrasing is, because if we just wrote the probability that all 20 have no problems, then
Because
it's easy.
it already says that only 15% have no problem. So it
Exactly.
would
So
be
that's your
0.
P. Right. So now you know P is going to equal 0.15, right? Your sample size N is 20, and your successes are also 20. And you throw that into the binomial, and away you go.
Okay.
What was your second one?
Going through the, I can't say it in French, the Poisson.
Poisson. Yeah, you can just say poison.
Yeah, that one. So that was
451, I think, is what the first one, where it asks you to do the approximation.
Yeah, part C. Yeah.
Yeah. So what you have to do is you first have to compute a few things, right? Because we're approximating the binomial, so we need to know what the average is, right? So in this case, mu means mean, right? Is n times p, and for this question, it's 2,500, right? Because it says 2,500 hits per day,
Mhm.
and then a success is 1 out of 1,000, so that's times 0.001, and then that gives us 2.5.
Mm-hmm.
So what that tells us is on an average day, they make 2.5 sales a day,
Mm-hmm.
right? Because they get 2,500 hits, and only 1 out of 1,000 people, 1 out of 1,000 hits results in a sale. So they get 2.5 sales a day. That's what that's telling us on average.
Mm-hmm.
So now they're asking us to find the probability that the firm will have more than 5 sales, right? So they want the probability that our successes, right, our number is greater than 5, which is really 1 minus the probability that X is less than or equal to 5. Because with all these things, whether we do the Poisson or the binomial or whatever, the CDFs are always cumulative. They always go from 0 and up. So if we want greater than 5, well, here's 5. If we want greater than 5, everything up here, then we're going to have to calculate less than or equal to 5, right? So 0 through 5. So we're going to do a CDF of the Poisson with X equaling 5 and our mu equaling 2.5. And then when we get that answer, we got to do 1 minus it.
Mm-hmm.
And that's how we do that one.
Okay.
So in SAS, right, we've got to get the SAS code up. And so we've got right here, the Poisson, right, for 1 outcome. So that's the PDF. And then we've got the, for outcomes of X or less, right, that's the CDF. So we're going to use this one. We have N is our number of successes, right, which is 5. And then M is our mean, right? So M is mean, N is value of interest, right? I just took this coding out of the book. I probably should have changed this to X, because X is normally when we talk about value of interest, but it doesn't matter, right? As long as this letter is the same as this letter, the code would work. But anyhow, in any case, if you run this, it gives you that number, and then remember we have to do 1 minus that to get what we're looking for.
Okay.
Dr. McBride, I have a quick question.
Go for it, Cheryl.
The first question that that we talked about, that Mary Beth had a question on.
Yeah.
4.46a.
Yeah.
Isn't it all of the 20 returned products have some type of problem?
No. Oh, well, yes, A is, but
yeah.
she was asking for D.
Oh, of D. Got it.
Yeah.
Got it. Okay,
Yeah.
So my bad.
No. You're absolutely right. You were correct in what you said, that all the 20 had some sort of problem.
So that
That's
would be
part A.
85% and not 15. So I was confused.
Yes, exactly.
I didn't realize it was D. Got it.
Yeah.
Yes, D is 15%.
Yep.
Okay.
Yeah, A and D are pretty much the same question. A is just 0.85 raised to the 20th, and then D is just 0.15 raised to the 20th.
Yeah. But when I run that through the binomial process, D, I mean, I get like a number to the negative 17th. So that essentially is like 0.
Yes.
Okay.
Yeah, it gives it to you in scientific notation. It's so small that it's got 16 zeros before it. So yeah, it's basically equivalent to 0.
Okay.
So what that tells us is it's damn near impossible that all 20 of them, right, are going to be fine.
Right.
It means we're guaranteed that we're going to have at least one defect of some sort.
Mm-hmm.
Okay. Anybody else with week 4 stuff?
Hi, Dr. McBride. Sorry, I can't talk. This is Alpi.
Yes, Alpi.
On 451, question B, what conditions must be satisfied? I thought that was the sales have to be consistently 2,500 a day, or the calls, the hits have to be 2,500 per day.
Yes, it's you could word it a couple different ways, but yes, you have to have basically the probability of a sale has to remain constant. So whether you phrase that as you have to have a consistent 25 hits per day with 1 out of 1,000 or whatever, but it boils down to the probability has to be consistent, has to remain constant.
Got it. Thank you.
But you also have one more thing. Does anybody know what the second constraint is, or the second condition?
The hits are mutually exclusive from the sale.
Yes and no. You're close. It's not so much that the hits are mutually exclusive, the hits are independent, which I think is what you meant. An independent sale means that, or the hits being independent means that one person buying has no influence on the next hit. All the hits are independent. So it's like flipping a coin, right? All flips are independent. It doesn't matter what outcome comes from the first flip. The second flip is still going to be 50-50 tails. And if you flip that coin 10 times and it comes up tails 10 times in a row, that 11th tail is, or that 11th flip is still 50-50 heads or tails, because they're all independent. It doesn't have any kind of memory. Mutually exclusive means that, and students get these two phrases mixed up a lot. Mutually exclusive means two things can't happen at the same time. So if you said hits and sales were mutually exclusive, that would mean you couldn't have a hit and a sale at the same time, but that's impossible because you couldn't have a sale without a hit, right? So they're definitely not mutually exclusive, but that's a very common misuse with those phrases because they're very hard to understand and very easy to get those mixed up. What we're looking for is independence.
Okay.
Awesome job, guys. Anything else from, excuse me, from week 4? Sound like Peter Brady all of a sudden. Okay, well, if nobody else has any questions, and if you do, speak up, but we'll go ahead and answer Mary Beth, or was it Cheryl had 2 from week 5? I can't remember.
I have 1 from week 5. Mary Beth might too. I'm not sure.
I just couldn't remember who asked at the beginning. Go ahead, Cheryl.
So 4.65D. I kind of used the binomial, but I kind of cheated where I just like figured out the X.
Right.
But so I figured out the X was a number, 263, to get me the probability of 0.6. So I want to know if I just added 13, basically because X is 263. And if we start with 250, then K to me would be 13.
13, yeah, right.
I just, is that correct? Because I actually went like 250, 255, 260. Oh, no, it's close, 261, 262. You know what I mean? Just
yeah, totally. No, that's
it through the program.
That's great that you're thinking about how to do it, and that's fantastic. You're close. The only reason why your answer isn't completely correct is because for this one, we were supposed to do it as a continuous random variable and not a discrete random variable.
Okay.
So we're no longer working with the binomial with this question. We're working with normal distribution, right? It says, let it be a random variable having a normal distribution. So basically, visually, this is what this question is asking for.
Okay.
Here's my normal curve. Boy, that's a great looking normal curve. Woo. Here's the mean, right? Because the mean is always right in the middle, which in this case is 250. And if we go out some distance in both directions, right? So if we go up a distance of k and down the exact same distance of k, then within this interval is supposed to be 60% of all of our data.
Okay.
Now, according to the empirical rule, if you guys remember the empirical rule, we talked about that in a previous homework. If we go 1 standard deviation in both directions, what percentage of our data should be trapped in that interval? Does anybody remember? I don't want to put just Cheryl on the spot. Anybody else can chime in.
Say that again.
So the empirical rule says if we go 1 standard deviation in both directions, we get a certain percentage.
66.7.
68. Yes, very good. You're very, very close, Salpant. Well, I don't know where you got 66.7. That's interesting. I think you were probably getting 68, and then the last one, which is 99.7, kind of confused. So the empirical rule, yes.
Yeah.
So the empirical rule is 68, 95, 99.7. So if you go 1 standard deviation, you get 68%. If you go out 2 standard deviations, you get 95% of the data. If you go 3 standard deviations, you get 99.7. So if we want to capture only 60%, which is less than 68, we at least know the answer is going to be smaller than 1 standard deviation. And they told us the standard deviation was 50. So we know the answer should be less than 50. But it should be pretty close to 50, right? You got like 14 or 13, which is way too small.
Okay.
So what we would need to do is we would need to work this backwards. Okay, so if there is 60 in here, how much is in just this tail? And take a second, think about it.
60, 30, 90, 30, 60.
Nope.
No, so if the, hold on.
So there's 60 in this bit. How much is under the entire curve?
100.
100, and we know it's perfectly symmetrical, right? So we know half is below the mean and half is above the mean. So if there's 60 in here, we know there's 40% left, and there has to be how much in each tail?
20.
Exactly. So we know there's 20% in here. We have a formula that goes backwards, right? So if we look at our SAS stuff, our SAS codes, we have this normal probability code, and you'll notice that we have the normal CDF, right? Where you give it an X, you give it the mean, you give it the standard deviation, and it spits out a probability.
I think I used that.
Well, that would be...
Came up with, because I kept changing X.
Oh, great. Yes.
Yeah, I kept changing X. And if I put X equals 263, the probability spits out at 60.
See, that was your problem. You didn't need a probability of 60. You needed a probability
of 40.
20.
20. Got it. Oh.
But if you're doing the big number, sorry, if you're putting a number bigger than 250, then you need 80. Right? Because if you're trying to find this number here.
I can't see your mouse. Okay, yeah.
If you're trying to find this number here, that's 60 plus 20. The area to the left of it is 80. So you have to plug in numbers until you get 80.
80%.
Yes.
Okay.
So keep plugging along until you get 80%. And then if you go down further, you'll see that you have this number here, or this formula, sorry, here. So look at the difference between these two formulas. Keeps jumping too much. Okay, so this first formula for normal stuff, right? We give it an X, an M, and an S, and it spits out a probability. In this one, we give it an M and an S, but instead of an X, we give it a P. So we give it a probability, and it spits out a value. So this is the opposite function of this, right? So in this top function, you kept giving it different X values until you found one that gave you 80. Well, guess what? You could just come down here and put in 0.8 and run it, and it's going to spit out 292.
Cool. Okay. Yeah, I was using the probability and not the quantile. That's awesome.
Yeah,
Okay.
well, I love that you were using the probability because that is great. That's just a hunt and peck version, right? You
Yep.
just kept putting in, and you could do that, right? We could keep putting in numbers in here until we got it closer and closer to 80. You know, like, okay, we try 250, and then we try, you know, 275,
Yep.
and we run it, and we go up 0.69. We know we need 0.80, right? So we keep getting bigger and bigger until we get the right value. This just gives us a more accurate one because, as you saw, it gives us even decimals, right? So the true value would be 292.081, but of course we're dealing with a scenario where, you know, we only have whole numbers. So you would just say 292, and then you go, okay, well, that's 42 above 250. So now you know that K is 42.
Okay. Cool.
Make
That makes
sense?
yeah.
Awesome. And kudos for working ahead. That's fantastic.
I think I've got one more question.
Okay, let me just make sure. Does anybody else have anything from
Okay.
chapter 4? Okay,
I'm sorry. I
go
just
ahead.
thought of something for
Yeah,
in chapter 4.
go for it.
And I just don't know if I'm wording it correctly. It makes sense in my head.
Sure.
But looking at 421 part C.
Let me bring it up so I can see it. 421 part C. Yeah, go for it.
So in my mind, it makes sense that they're not independent because a donor can be white and have type O blood.
That really is the English way of describing it. Probabilistically, in order for two things to be independent, for something to be independent, the probability of the event, so T1, given that somebody is white, has to be equal to just the probability of T1. That would make them independent. And of course, if you calculate these two things, they are not equal, and so they are not independent. And your idea of, well, of course, someone can be both things. See, again, that's where people get independent and mutually exclusive confused. Being independent doesn't mean mutually exclusive. Like, you can have an overlap and still be independent. What independence means is that if you're told somebody is white, then the probability of them having, what is T1? Type O blood doesn't change at all from just the probability of the entire population having type O blood. So what that would mean was that type O blood would be evenly dispersed amongst Caucasians and the general population, right? So if in the entire population of human beings, 20% of the people had type O blood, and also within the Caucasian population, it was 20% O, it didn't necessarily mean that it had to be 20% in the Asians and 20% in all the others, right? It just had to still be 20% overall and 20% for whites. Then these two probabilities would be the same, and that means these two events, having O and being white, are independent because given the condition of being white doesn't change the probability of T1.
Okay.
So
That
that's
makes
what
sense.
being independent means. It's not a mutually exclusive thing.
Okay. Thank you.
Yeah. All right, cool. So we still have time for Cheryl, your last question from week 5, I'm assuming.
Yes. And I think we may have already answered it. I just want to confirm.
Okay.
This is 472B.
Yep.
So I did use, again, the probability.
Yep.
And so I found the top 75% and the bottom 25%. And they fall between 472. Oh, hold on a second. I'm looking at 4. They fall between like 600 and 425, basically. But I guess the real question is, what do we call this value?
Yeah. See,
Is that
this
okay?
wording is really confusing because these two numbers mean the same darn thing.
The bottom 25 and then the top 75. Yeah, so you're getting the scores from the top 25% of the curve, and then you're getting the scores from the bottom 25% of the curve. But the
Nope.
middle piece,
Nope.
right? What you
Nope.
want? No?
Because read again, the top 75%. That means I have an X.
Okay.
And the top 75% is here, and the bottom 25% is here. I only have one X.
Oh.
Yeah, I know. This is what everybody
Okay.
thinks it is. Everybody thinks that they're looking for two values.
Yes.
This one that has 25 below it, and this one that has, right?
Yeah.
That's not what you're looking for. This is not it.
That's not it? Okay,
No.
good. So then the math is wrong. So now I don't know what is that called the lower quartile?
Yes, that's quartile 1 or the lower quartile. Very good. That's
Cool.
exactly what
Okay.
that is. Yeah, and then if you wanted to do it in SAS, right, we could use
Yeah, I got it.
the same one we did before and put in
Yes.
0.25.
Yes. Okay, sweet.
Very good.
One other thing. Quick question. The
Yep.
very end question where it asks you to complete the correlation coefficient, but it only gives you one statistic. So you can't really correlate. I didn't understand because
No, it's because you do a QQ plot and then you get the correlation coefficient and p-value for the QQ plot, right?
No, I did the QQ plot and the p-value comes out to 0.75, but it doesn't have an R value. Is there a different, like I thought the correlation coefficient meant you needed two statistics or two types of variables.
You do, but when you create a quantile plot, what it does is it calculates the quantile for each of your data values, right? So
yes.
So here's all your data values lined up, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this is the 1/15th quantile as a decimal, right? And the 2/15ths and right? So this is the 100th quantile, and so on and so forth. So when we're talking about, or just one, right, or 100%. So it calculates all of these percentiles for all of your data.
Mm-hmm.
And then what it does is it maps these things, like these are your pairs of data. So it maps 0.47 with 1/15th, 0.58 with 2/15ths, 0.67 with 3/15ths, and so on and so forth. So there are your two sets of data, and then it calculates the correlation between those two sets of data.
So in SAS, then what am I checking to see that value?
When you run the QQ plot, there's a thing in the options where you have to say, inset, I think it's like inset data, and you click on that, and then it like asks for the type of data or something, and you click on, I think correlation and something else, and then it should show it.
I didn't see that, and I checked all of them.
Okay. Let's see, we've got. Remind me again, is it under distribution analysis?
Yes.
Is the quantile plot? Yeah. Okay, so I'm just going to run it on this data just so I have something. Okay, so change this to import, pick my variable, expenditures. Okay, under options, don't need histogram. We want to check for normality, so we're going to do a normal quantile plot We're going to add insert statistics under inset statistics. We're going to do the goodness of fit test.
Mm-hmm.
And that
I
should,
took mean, median, standard deviation, and that gives you p-value, but it doesn't give you the correlation.
all right, let me see. Oh, the test statistic is the correlation.
Ah, got it. Okay, cool.
Yeah.
I already did
Yeah.
it then.
Yeah.
Okay.
Yeah, that is your correlation. They just, because
Okay.
it's a goodness of fit test,
Okay.
the test statistic is the goodness of fit, i.e. your correlation.
Got it.
That's why they call it that.
Got it. Okay. Because I was used to doing the correlation coefficient under correlation analysis, which required two variables.
Correct. Yes.
So in this case, it's just the test statistic.
Yes.
Okay. Very good then.
Awesome. Okay. Well, that's 601. So are there any last minute questions? All right, guys. Excellent class. Thanks for showing up. And you're all welcome to show up tomorrow as well if you have more questions.
Thank
Thank
you.
you.
Thank you. Good night.
Thank you.
Good night.